Hi, everybody. I hope you're doing well. Today, I want to talk to you about the kinetic molecular theory of gases. The kinetic molecular theory of gases is one of these moments in physics where we bring together a bunch of really big ideas. This is an opportunity to take a look at mechanics and thermodynamics and how they are interconnected. I want you to imagine that we have a balloon, and this balloon has a gas molecule in it, one gas molecule, and that gas molecule is moving over and it hits the edge of the balloon, and then it bounces back towards where it came from. And we are going to use that as the basis of our understanding of the kinetic molecular theory. So I'm going to start the kinetic molecular theory discussing the momentum of this molecule. And so we know that the change in momentum of an object is equal to the mass times the velocity final minus the mass times the velocity initial. And so when we are talking about this gas molecule, it's one gas molecule, so the mass is the same, but the velocity final and the velocity initial are also going to be the same. When we're talking about molecules and gases in the last chapter, we talked about them being ideal. We're going to treat this as ideal, that there's going to be no loss in energy with the collision as the molecule hits the wall. So the velocity in is equal to the velocity initial is equal to the opposite of the velocity final. I'm going to make it negative V initial is equal to V final here. And so the change in momentum means that, or we could write it the other way. We could write it as V final is equal to negative V initial, whichever way you want to write it, or we could write it, and I'm just saying this just so that we're all on the same page, V initial is equal to negative V final. Again, however you want to write it, it doesn't matter, but we're going to substitute this in right up here. And when we do that, what we are going to get, the equation we're going to get next is that delta P is equal to mv final minus negative mv final. So the velocities, the two negatives cancel out. And so we're just going to say that the change of momentum is equal to mv times 2. I'm just going to call it mv at this point. I'm going to drop the whole final and initial piece and because the velocity hasn't changed. So whatever the velocity is, the change of momentum is 2mv. Now, we also know that when we talk about momentum, that the change in momentum is equal to force times time. Just we're going to keep this equation on the back burner for right now. That the change in momentum is equal to force times time. That means that force is equal to delta P over T. Now, with that, we also know that the average velocity is equal to the change in position divided by time. Now, I want you to think about this collision here. An object comes in, and then it comes back to where it came from. That means that it would be x in, and it would be x out. So that means that if it starts at a point, goes over, and comes back, that's 2x. So v is equal to 2x divided by t, or we could say, in this particular case, v times t is equal to 2x, or we could say that t is equal to 2x divided by v. That's the one we're going to want to use, because what we're going to do is we're going to take this and plug it into here, and we're going to take this and we're going to plug it into here. And when we do that, we are going to get 2 mv divided by 2x divided by v. That simplifies down. When we go to simplify that down, that's going to simplify down into the 2's are going to cancel out. The v is going to, it's in the denominator, is going to come up to the numerator. And so we're going to get 2. I'm sorry, they just mentioned that the 2's cancel out. We're going to get here mv squared divided by x. Okay, the length. And that's going to be something we're going to use. And again, that is equal to the force. Now, another concept that we deal with is we deal with pressure. Pressure is equal to force over area, which is equal to, as you know, force divided by x times x, or force is equal to x squared, length times width, whatever that happens to be. As you might have guessed, we are now going to bring this down into here. And when we do that, we end up with F. I'm sorry, we'll do that again. We just had F. We're going to get mv squared over x divided by x squared. And as you probably are realizing, that's x squared over 1. So we inverse and we multiply. And so when we do that, we get mv squared over x times 1 over times the value of 1 over x squared. So we get mv squared over volume. That is where we're going to end the origin of pressure. Now, we're going to take this a little bit further, and we're going to talk about how this leads to our understanding of speed. And so we want to imagine for a second, and this came to us from James Clerk Maxwell, that in the balloon itself, there are molecules traveling in all different directions. There are some molecules traveling up, there's some molecules traveling down, there's some traveling to the left, there's some traveling at diagonals. We want to keep that in mind. But if we average all of that up, we have velocities in the x direction, velocities in the y direction, and velocities in the z direction. That there's a certain probability that a molecule is traveling in any one of those directions. We just want to look for now at the velocities in the velocities in one direction. So let's just say we have the velocities in the x direction. So the way we figure this out is that we are going to take this equation that you see on the screen in front of you, where we have mv squared, where this is velocity and this is volume, over volume, and we treat it for a lot of molecules, an n number of molecules, because there's not just one molecule floating around, there's a lot of them. So the total pressure is going to equal n times mv squared over volume. And this is, we're going to treat this as the average velocity, because some molecules will be going faster and some will be going slower. And so this then turns into n over volume times mv squared, just in the x direction, average. Because what we've done here is we've said that we're only looking at the pressures in one direction at this point. And we've taken all of the molecules, and there's a certain probability, so n times the equation, and then we pulled the volume out. Now, these average velocities would be something like v squared is equal to vx squared, so vx squared plus vy squared plus vz squared. This is, and then you would take the square root and find the average velocity. And so the average velocities end up coming out in what is called an equivalent, and that each of these would have an equal probability. There's an equal probability this one's happening, there's an equal probability this one's happening, there's an equal probability this is happening. So they're all the same. So this would be like adding up v squared. This would be like adding up v squared plus v squared average is equal to 1 plus 2 plus 3. So the net average is 3 v squared. And since we are going to be solving this, now this is this out here is the average velocity, the net average velocity of all x's and y's. And again, we have a certain probability that some are going in the x direction, we have a certain probability that some are going in the y direction, a certain probability some are going in the z direction. And so if they all have the same probability, then it would be 1, 2, 3. So v squared average is equal to 3v. And therefore, the average of just the x's would be 1/3, or v average x, and again, this is squared, is going to equal 1/3 of this. The net v average of all motion, 1/3, all motion squared. And that is going to then find its way up into this equation, because now we have a value for Vx. So when we rewrite this, we get pressure is equal to N divided by volume times, again, probability of things happening, 1/3 of the velocities, M times 1/3 of all of the V averages. This up here was the pressure in the x direction. We're saying this is the pressure in all directions, because we're looking at 1/3 of it in there. And that means that we end up with, that's squared, we end up with a simplified equation where I bring the 1/3 out. I could make a simplified equation. Now this leads us to what, again, we're referring to as the kinetic molecular theory of gases. Right now we have a simplified equation which says P average is equal to 1/3 N over V times mv squared average of all the motion. Now we're going to use our brains for a second, because we know that mv squared looks like something we know. Mv squared is equal to, looks like kinetic energy. 1/2 mv squared is kinetic energy. Well, in mathematics, if we multiply by 1, we do no harm. So if I multiply by 2 times 1/2, then I really get 1. So I can take any number. Like if I take the number x plus y equals z, and I multiply both sides by 2, I haven't done anything wrong. I can multiply the other side by 2 again. I haven't done anything wrong. I haven't changed the meaning of the equation. If I multiply this side by 500 times 1 over 500, that does nothing to the left side, because I'm really just, that's going to cancel out. If I multiply 2 by 1/2, it does nothing. But why would I do that, you say? Well, watch what's going to happen. So I'm going to plug that in up here, and I'm going to get P is equal to, I'm going to make that 1 a 2. I'm going to multiply by 2, 2/3 NV times 1/2 mv squared. Now you might say that this looks weird, or that this looks like we're playing a trick, but reality, what we have just done is we've said that the pressure is equal to 2/3 N over V times the kinetic energy of the molecule, the kinetic energy of the molecule. From there, we're going to bring this down. And when we do, we get an equation. And you may have been able to see this already, but we get an equation where we can get P times V. I've taken the V from the left side. I get P times V is equal to the 2/3 times 1/2 squared, and I get 2/3 n, because I multiply both sides by v, times 1/2 mv squared, or we can just call this the kinetic energy. And what that tells us, we know already the idea that we already know the idea from our chemistry courses that PV is also equal to nRT, but we also know that an alternative way of representing this, instead of representing it in terms of molecules, we can represent it in terms of moles. And so we can rewrite this as PV equals nKT. This is called Boltzmann's constant and Boltzmann's form of the equation. And so we can rewrite this whole thing to say PV is equal to nKT which is equal to 2/3 n times the kinetic energy, 1/2 mv squared. The n's cancel out. We have a constant in here. Just remember, a constant just makes the equation work. It balances the equation. And so that ultimately means, this is what the big takeaway from this, that ultimately means if nKT is equal to 2/3 n times 1/2 mv squared, that's what we say over here, 1/2 mv squared, 1/2 mv squared, then the K value, again, constant. So that means T is equal to 1/2 mv squared. And this thus proves that temperature is equal to the kinetic energy of the molecules. And so if temperature is equal to the kinetic energy of molecules, that means that the faster the molecules are going, the greater the temperature is, thus proving what we refer to as the kinetic molecular theory of gases, that the velocity of a particle is equal to its temperature. Faster particles are going, the greater the temperature is. Now, along these lines, we have two other facts I want to bring to your attention. One is something called the root mean square. And the root mean square is a way of averaging. So in mathematics, we have a geometrical average, we have a arithmetical average, we have an average called the root mean square. And what that says is you would add together all your numbers, v squared plus v squared plus v squared, or a squared plus x squared plus z squared, or something like that. And then you take the square root in the averaging. So the root mean square is a version of that. So what we are going to do is we're going to take the root mean square velocity. The root mean square velocity says to add together all of your velocities. And that's exactly what we did here. We had the 1/2 mv squared. And so when we take the 2/3 n times 1/2 mv squared, and we simplify this down, and that's equal to nKT. What we find is that the n's cancel out. We bring a 3 over here. The halves cancel out. We divide the m over. So we get the V RMS is equal to 3KT divided by m, and we do need to take the square root of it because we're taking the root mean square. And what this is called is the root mean square velocity, 3KT over m. It tells you the average velocity of any molecule in the balloon, and it tells us that the hotter it gets, the greater the velocity is. The more massive the particle is, the less velocity it has. That makes some sense too. Now, this equation, this RMS equation, V RMS is equal to the square root of 3RT over M. That leads us to what is referred to as Maxwell's distribution. And Maxwell's distribution looks something like this. It's a bell curve where we have the number of molecules and the temperature. We're going to look at this with the speed down here and the probability over here of a molecule. And so what we find is that at a specific temperature, there is a probability, the greatest probability of finding molecules right in the center. It's the median value. The actual average value is slightly higher, and what's called the root mean square value is yet higher again by just a tad. This represents the probability that you're going to find molecules. So if I have something at, let's say, 350 degrees Kelvin, there is a probability I'll find I'll have a molecule at this speed. There's a probability I'll have it at this speed. There's a probability. As I get closer and closer, I get closer to the average. Now, why are the velocities less or more? Well, imagine these molecules, multiple molecules floating around. They're going to collide with each other. That's one of the reasons. And so some molecules are going to slow down, some are going to speed up. There's a probability there's a molecule that's not moving. There's a probability that there's a molecule moving so fast that it literally goes up and escapes our atmosphere. And what do I mean by that? Well, the probability speeds are going to be found in your book. And what you will find is that the probability speeds for different gases are dependent on the mass that they have. And so if I take carbon, which is not a gas, if I take oxygen, which is a gas, and I look at its velocity at room temperature, there's a certain probability that I will find a gas molecule that's not moving. There's a certain probability I find a gas molecule that's moving 1,000,000 meters per second. But the most likely probability is a velocity that's a little bit less than that. That's more reasonable. Oxygen at 11 at a temperature of about 1100 K only has a average velocity of about 800 meters per second. Well, here's where things get interesting. Let's say we have helium. The escape velocity of helium is greater than 11 kilometers per second. And that number should be ringing in your head, 11 kilometers per second. Why do you say that number? Well, because 11 kilometers per second was the velocity that a molecule or an object at Earth, if we threw it at that velocity, would escape Earth's gravity. So that means at room temperature, the velocity of a helium molecule is so great that it literally can escape Earth. And that is why we don't have any helium or free hydrogen just floating around on Earth. We have a lot of hydrogen in water, but when it turns into a gas, it just floats away. Why? Because hydrogen and helium are so light that at room temperature, they are moving so fast that they can escape Earth's gravity and disappear forever. They don't stick around in our atmosphere. And so we need to take a look at that. If you have any questions about any of this, let me know. We will talk again tomorrow.